Okay, so this is describing some of the work that CGI has been doing over decades, and part of it's already been alluded to by Francois and most recently by Nick. But so my name's Mark Rattenbury. I'm the chair of the Geoscience Terminology Working Group, so one of the working groups under the CGI umbrella. I'm going to speak briefly on our vocabulary stuff, followed by Michael Sexton, who's the chair of the Earth Resource ML working group, and he's going to be talking about that. And then to conclude, we've got Eric Boisvert, who's the chair of the GeoSciML Standards Working Group. So that's a CGI-IUGS joint working group. And he'll be discussing some of the ontology relationships that could be moved on from the GeoSciML standard. So I'm calling this an ontology in quotes. So, and I won't go, and none of us are going to go into the detail of what GeoSciML is, Earth Resource ML is. You'll see an element of that in Michael's presentation. But essentially, GeoSciML is about a logical model of geological features. So it's what you might see in a geological map or a cross section and stuff. There's a whole bunch of encoding rules for transferring some of that information. So it's effectively a transfer standard. And Earth Resource ML is a similar logical model, except it's in the mineral resource space, and Michael will expand a bit on that. And as was pointed out earlier, these are hinged or they utilize the CGI vocabularies that Nick was talking about. And in conceptual form, in the GeoSciML model up here in the top right, it's a complex model. You can look at one small part of it, and it's still complex. But each of these classes or entities have links to CGI vocabularies. In this case, we're looking at the simple lithology vocabulary. So this is a seminar which is about ontologies and knowledge graphs. So and I guess we haven't really talked about what an ontology is and what a knowledge graph is. And to be honest, it beats me sometimes. There seems to be a large number of opinions and definitions out there. So I'm not going to go, but I think the key thing is that they're similar in the sense that you're trying to relate a bunch of classes or entities, and they have attributes or properties, and there are relationships between them. So an ontology, the knowledge graph, they share those sort of relationships, and they work in different ways. And so and in a sense that the GeoSciML, the Earth Resource ML data models are describing these classes and entities, the attributes and properties and the relationships. And the CGI vocabularies are, again, they're adding value in terms of the attributes and the properties, and in some cases, some relationships. So Nick has shown you the published vocabularies, which are available on the CGI site. These are ones which are hosted by Geoscience Australia. There's 54 of them. These the GeoSciML ones, the Earth Resource ones. There's a number awaiting publication, and then there's another 50 or so which are in some stage of preparation. So we've done the bulk of the really important ones, the ones that are the most common needed for applications, but in terms of the more complex parts of the GeoSciML model in particular, and some of the Earth Resource ML, we've still got quite a lot of vocabularies to build. And as Nick has pointed out, the vocabularies have definitions, they have sources, and they can have synonyms, and in many cases we're building multilingual translations for some of our vocabularies. So you can see that in the HTML version of this record for talc, and you can see it's got an alternative label, soapstone here. It's part of a broader group of industrial minerals here. And they're also, and this hierarchical thing is not just about, it's broader and narrower terms. So you can have the basalt as part of a broader basic igneous rock, but it can also have a secondary broader group or another broader group, in this case, fine-grained igneous rock. And it can have a couple of narrower terms in this case. So it's hierarchical, and it can be one-to-many. Excuse me, I didn't mean to jump that too quickly. So I think excuse me, we must be on to you already, Michael, is that right?
Oh, Michael, I'm not
muted,
hearing
Michael.
Yeah, okay.
Thought I had unmuted, but I obviously hadn't. Thank you, Mark. As Mark said in his introduction, my name is Michael Sexton from Geoscience Australia. I'm chair of the Earth Resource ML Working Group. For my part of this presentation, I'll give a brief overview of the model and speak to our experiences implementing it and the limitations that we've encountered. So, as Mark indicated, Earth Resource ML is an extension of GeoSciML. It's a data model for mines and mineral occurrences and their resources, which contains those entities and their relationships. There are 19 vocabularies that are specifically designed for ERML, which control the attributes of the entities of the model. And the vocabularies include terms for mineral occurrence type, operating status, and other things like mineral commodities, amongst many more. Next slide, please, Mark. So a mineral occurrence is an entity. It's defined as a mineral accumulation in the lithosphere. It's an implementation of the Earth Resource class, which itself is generalized from geologic feature in GeoSciML. The mineral occurrence has an attribute type, which uses the mineral occurrence type vocabulary. And this defines the entity as anything from a mineral occurrence or a deposit to a project or a field. Next slide, please, Mark. A mine is an entity which describes an excavation for the extraction of mineral resources. It's related to a mining activity, which is the process of extracting the resources from those deposits, and those deposits themselves are represented by the Earth Resource feature type. Mines have the status attribute, which is controlled by the mine status vocabulary, including terms like operating, closed, care and maintenance, etc. Mining activity has the activity type property, which includes open cut or underground mining. Next slide, please, Mark. The commodity entity is related to both mineral occurrences and mines as an associated commodity of the mineral occurrence, so whatever resources might be found in the mineral occurrence, and as a product of the mine. The commodity has an attribute, which is also called commodity, controlled by the commodity code vocabulary, which is a SCOS vocabulary, and which heavily uses the narrower and broader relationships to group commodities together. Next slide, please, Mark. In implementing this model, we've encountered some limitations. One is the strict hierarchical parent-child relationship between mineral occurrences. A deposit may be a child of both a project or a field, but under the model, it can only be a child of one. Furthermore, a project or a field can differ in domain. So a field is essentially a spatial representation or a collection of mineral occurrences, which is not strictly time-bound, while a project is something that exists with a defined start and end date. So they don't really speak about the same thing, even though they're sort of in the same vocabulary. Next slide, please, Mark. And so for commodities, this vocabulary doesn't really capture the full relationship you can have between commodities. One example is uranium is classified as a metal commodity as its broader definition under SCOS, but it can also be considered an energy commodity. And that's probably its most important attribute. Uranium also has an oxide compound, U3O8, which is most often reported by exploration companies. Its relationship to this oxide can be represented by a mass conversion factor, which we don't have in the SCOS vocabulary. And other commodities, such as bauxite, may have other commodities as end products or mid-stage products, such as alumina and aluminium. But these relationships are, again, not captured in the SCOS vocabulary. Thank you. Next slide.
Oh, I'm Eric Boisvert from the Geological Survey of Canada, out of Quebec City.
So I've been, I will talk about a bit the first experiment of creating ontologies for GeoSciML. So the first experiment was really trying to extract the information that we have already in the schema and the vocabularies that we have encoded into UML. So the first experiment was really driven by BRGM in France by Abdel Felechi, and there's a rule. There's actually a specification of translate a UML into OWL. It's called the ISO 19150-2, and as so people who have been working in OGC knows that we have some sort of a process that turns the UML into XSD, so which is basically the XML encoding that we use for transferring. So there's also a transformation rule for the same for transforming the UML model that you've seen from Mark and Michael into what the language that we usually use for representing knowledge, which is how which is an RDF based language. So the first experiment was really made based on the UML model, as I mentioned, but there's a couple of issues doing that, simply because the UML model does not have all the richness of a knowledge representation. It's really meant for creating a transport model, so an interchange format. So that first experiment, we used shape change to apply those rules on the UML model, and because there are so many things missing into the model that are not explicit or are not encoded at all, some manual edit were required. So the result of that experiment is available on GitHub. So you have a document written by the RGN team explaining all the issues that we'll go through. So there's a couple of the first real issues about the doing that is it's basically a conceptual issues, because what you're really describing at this point is a transport model, not geology. Simply because the UML that we've created has a lot of artifact of creating an XML file, and also because it's been created as a transport mechanism. So it's basically structural. So it structures the information across the file. So the resulting ontologies has a lot of idiosyncrasies that you find into UML. So you're describing the UML model, you're not describing geology. And also some other aspect of GeoSciML is the schematic, the way that you encode in a file format is distinct from the vocabulary work. So there are two important parts in GeoSciML. You have the schematic and you have the vocabularies, and these things are two different governance. So the way that you the way that the schema for GeoSciML is made, it basically allows other groups and other organizations to create their own vocabulary, as Nick presented earlier. And there are also a couple of technical issues related to the way that OWL works and how UML works. So next slide, please. So some of the first result of that experiment is that there are a couple of issues related to use the UML version that we have published as a standard as a canonical model. So a canonical model is a model reference that everything derives from, because really it was created to document a transport model. Of course, there are some semantic, there are some ontology and knowledge representation, because it's really about geology, but it's limited to its use, which is really a transport model. So there's a lot of expressiveness in OWL that are not covered in UML. It could, so you have ways in UML to add parameters and properties and stereotypes that you could actually describe what you want into the UML model. It hasn't been done because that was not the purpose. So that's the important distinction at this point. So this is a description, a knowledge description of the UML model, which is a transport model and not the conceptual model of geology. And this the big part that we're missing is really the richness of the vocabulary when you do that. So next slide, please. So an example of a couple of examples of issues that you will have just using the UML as being the knowledge representation for your OWL. And there's a couple there. First, you see those blue boxes, which are they are data types. And this is just a trick in UML that you do just to package your properties. And they are not real things. They're just tricks to organize stuff. So for OWL, they just you have to tell your knowledge representation that these are tricks and not real things in the world. Another example is that you see in the bottom box in geological unit hierarchy, you have the role properties, and you also have a role properties in composition part on the right hand. So they are the same, they basically have the same meaning, they are roles, but except they have different vocabularies. And the thing in OWL, properties are first-class citizen. So they are basically defined on their own, they are not constrained by the class. So for UML, the role in geologic unit hierarchy is totally different from the role in composition part, but in OWL, a role is a role. So now you have a problem because they are constrained by two different things. They are constrained by two different vocabularies. So you cannot, you basically have to cheat here and just create two roles. One role, which is geological unit hierarchy dot role, and the other one would be composition part dot role. And this is some of the issues that you have while making these conversions. So some tools will do it automatically. We'll just add a dot and just create two different roles. But now you have discrepancies between the UML and the HAL because you're using two different names for some things that are the same name in the model. So another example, next slide, please. Another issue is the we have a light version of GeoSciML that was really meant for a simple application, essentially it's equivalent of a shapefile. So it's flat, it's really made like an Excel file, and you can see in that description that everything are character strings because really, again, it's a transport model. It describes how you would organize your file as a shapefile. So if you try to make an OWL representation, a knowledge representation of this thing, everything are strings. Of course, as human, we can see that they are different things by the name of the properties, but the machine can't. So Abdel basically had to go manually and just bind back all those properties to the right constraint because right now there's no constraint, they are just strings. Next slide, please. So as I explained, the vocabularies are really where the richness of geology actually sits because the schema is just a way to organize the values into the file. So right now, GeoSciML schema does not include vocabulary in the schema and the specification at OGC. This is something that IUGS manage. So right now, the vocabularies that has been thought of are expected in the current HAL implementation they were basically a mixture of SCOS and other vocabularies. So Nick presented part of it with the time scales ontology. So you have a mixture of SCOS. SCOS is really a description of labels of word, and they can be organized into hierarchy. And Michael basically pointed out that there are missing mechanisms in there that you can connect some part of the vocabulary to other part of vocabulary, such as the way they can constrain it. So one example, in GeoSciML, really, you can say that the granite is made of bits of T-Rexes, and the schema won't complain about it because it just transport the information. So of course, an ontology should probably be shocked by this because it's not possible. Obviously, you cannot have as organism into an igneous rock. So the way that they are organized right now, so the vocabulary are a self-contained list of terms, but they can be extended if you add some knowledge and some constraint that say that igneous rock is not supposed to have fossil and some events cannot be the source of some other rock types. And this is the kind of work that needs to be done. And I think that Boyan and Steve will present that, and some other people have actually done that. You have a lot of people, if you look at the publication and the literature, that the first thing they've done when they look at the GeoSciML standard, they really went straight to the vocabulary to start building their ontologies. So so really the conclusion here is that the ontology made on top of the schema is really a subset. So you have a limited amount of real reasoning that you can make on top of it, and the real richest should be from the vocabulary. So that was basically my message. Thanks.
Okay, I think that's us, Harvey.
Sorry, Mark, that is the completion of your presentation?
Certainly, yes, yes.
Very good. So thank you, Mark. Thank you, Michael. Thank you, Eric. Is there discussion, please?
Yes, it's Nick here. I'd like to rush in very quickly and just say, Eric, thank you for that excellent description of UML OWL issues. So in addition to the work with the ICS, I've got two roles that relate to that. One is I'm actually the Group on Ontology Management Convener for the TC211, so that's part of the International Standards Organization. And then in the OGC, I'm involved in model-driven standards. In both cases, what we're really verging on is shifting away from using UML as the model for everything to a more powerful modeling tool. And my contention in both of those arenas is that OWL is the tool for that. And I'll put a link in the chat in a minute that shows a standard that is model driven from a set of, not just one, but from a set of OWL models. There's an OWL model for the structural document. There's an OWL model for the domain that the specification is about. There are OWL SCOS models for vocabulary terms. There's many things in there. But the problem I have is that I can't, for instance, in the GOM community really move at all because there is this fixture on UML and people say you can do anything you like as long as you take the UML and convert from that. But when the UML just doesn't contain the semantic information that you need, you just can't do that. So we do have to have an information model there that is a superset of every other form that we needed. So if we wanted to convert down from something outwards, we have to have something that's richer than the UML we've been dealing with. And in time, I think we will produce UML-like pictures automatically from our models. They probably will look good enough that UML adherents will be happy with them, but we have to have a semantically richer superset to work with in the first place. And at the moment, the ISO does not subscribe to this yet. Yeah.
You know, you basically have to invent your own stereotypes and just overload the UML diagram just to put all the information. But at the end of the day, you just ended up creating an OWL model. So
you've created it out. Yeah. Look, I'm thrilled that you can articulate this. Not many people can talk about what UML is really doing and what OWL's doing and then compare them well. So thank you for that.
We had a stormy meeting in Orléans about the difference between OWL and UML. So it's an epic reference to that meeting. That Boyan was there.
More discussion, please.
Yeah. Thanks, Eric. I thought that was a great differentiation between the limits of a transport model versus one that's more semantically enriched. And I think that's a really important point to understand that, you know, until recently, technologies have taken us to the point of being able to structure digital information adequately in order to transport it. And that's been more in the foreground, and the actual meaning of the things that have been transported have been more in the background. But I think you know, more recent technologies now related to ontology allow that to change. And that's a really important distinction. So that was really well brought out. Thanks, Eric.
More discussion, please.
If Michael's if Michael is interested, I should say that at the moment, some of the limitations in what you can represent in the CGI vocabularies, I mean, that's a limitation. It's got sort of two fronts to it. One is that is what the implementers of those vocabularies wanted to represent at the time. But there's another limitation too, which is a tooling limitation. If we put more stuff in there, will the tools cope with it? I can say that if you were to decide, if CGI and others were to decide, look, we really want to do SCOS plus, we want to retain the SCOSness of our vocabularies, but we wanted to do things like include, you know, other notations for the chemical things in there, or conversion factors, or, you know, all of the other things that, you know, some extend the modeling that is around, not just a concept now, but, you know, more things. We wanted to strongly type the individual elements in the vocab, so that this vocab is not just about concepts of rocks, it's about rocks. This one's about not types of, not concepts of types of mines, but actual strongly typed mine types. If you wanted to do that, we could extend the tooling quite easily to cater for this. So we've got a few instances of that tooling now that caters for SCOS plus vocabularies. And mostly SCOS, they use SCOS to sort of organize the hierarchy, but then there's this long list of other fancy properties. And in fact, in the case of the British Oceanographic Data Centre's vocabulary system, they actually have different views of the same content coming through the same system. So just bear that in mind if you want to extend those vocabularies.
Thanks, Nick. Yeah, thank you.
Well, and actually, you know, this whole notion of vocabularies illustrates this whole problem of shallow semantics versus deep semantics, because in actual fact, vocabularies in the way they've been used in UML modeling and also related XML formations are really just artifacts. They're not real. I mean, the fact that you've created a certain structure that says it has certain slots in it and you need to fill those slots with certain terms is an artifact of your technology. You know, semantically speaking, these are all just concepts that are organized. I mean, the fact that you have materials that are granitic rocks and there's lists of various types of rocks doesn't necessarily say that that's supposed to be a list of things that you might call a vocabulary and should be managed separately. They're just one big pool of geological concepts that interact to form the knowledge base of geology, but our technologies have created this separation artificially. But this is an artificial separation that doesn't necessarily need to exist any longer.
Well, I think I partly agree, Boyan. I wouldn't say I wish it didn't have to exist any longer, but I think it does from just a governance point of view. Yes, sort of scientifically and ontologically, maybe not. But you know, when we go to a geological organization and try and move them up a semantic sort of enhancement pathway, if we say, look, present your vocabularies or present anything in a semantic form, it's usually easier for them to find, you know, the person that knows all about coal and then organize all the coal information there in a set of coal things, and then the next person who knows all about igneous rocks or whatever. So I do agree with you that we're on a pathway to getting rid of some of these artificial things, but I think that they exist for governance reasons more than ontological reasons. Yeah.
Yeah, but I wouldn't treat them as, I mean, vocabularies have been treated in the past as thesaurus-like entities, which are lists of words with somehow detached meanings, right? And I think we need to get away from that. What we're really talking about is treating them as separate modules, separate semantic modules that people can work on independently. So to that extent, I don't disagree that you need to modularize things. But this whole notion of treating, you know, one thing as structure and the other thing as a list of words as part of a larger knowledge organization, I think is no longer necessary.